Assalamualaikum and very good afternoon. Hi everyone. Continue with the topic standard Proctor test. Standard Proctor test is used to determine the compaction of different types of soil and the properties of soil with change in moisture content. It also used to obtain the maximum dry unit weight and also optimum moisture content. This laboratory test generally consists of compacting soil and non-moisture content. The test equipment use mold and a hammer. The soil is mixed with varying amounts of water and then compacted into three equal layers by a hammer. Each layer will be blown with 25 blows with hammer weight around 2.5 kg. From the standard Proctor test, the unit weight can be obtained. Unit weight is the weight of the soil per unit volume, and the relationship of unit weight, dry unit weight, and moisture content can be given as formula below. The dry unit weight is the moist unit weight over 1 plus moisture content. Standard Proctor test equipment consists of a mold and a hammer. The mold is diameter around 114.3 mm with the height around 116.43 mm. Meanwhile, the hammer weight of the hammer is 2.5 kg with the drop 300 mm.
The civil engineer, it is important to have the type of soil with the greatest shear strength. A better shear strength would be achieved by compaction. For the standard Proctor test, you will need the following materials: compaction rammer, mold assembly, brush, rubber mallet, trowel, wrench, straight edge tool, spray bottle. You will also need a number 4 sieve, a metal pan, and coarse-grained soil sample. 2 tin cans for the moisture content.
To begin with the procedures, you must first record the weights of the metal pan as well as the mold assembly. Pass enough of the prepared soil through the number 4 sieve to yield approximately 6 to 7 pounds of minus number 4 material. Cover the sieve and shake to remove the unwanted large particles. Place the prepared soil in a larger metal pan and add water accordingly. Prepare at least 4 specimens having water contents such that they bracket the estimated optimum water content. A specimen having a water content close to optimum should be prepared first by traditional additions of water and mixing. Select water contents for the rest of the specimens to provide at least 2 specimens wet and 2 specimens dry of optimum and water contents varying by at least 2%. 2 water contents are necessary on the wet and dry side of optimum to accurately define the dry unit weight compaction curve. Some soils with very high optimum water content or a relatively flat compaction curve may require large water content increments to obtain a well-defined maximum dry unit weight. Water content increments should not exceed 4%. Compact the specimen in 3 layers. After compaction, each layer should be approximately equal in thickness. Prior to compaction, place the loose soil in the mold and spread into a layer of uniform thickness. Lightly tamp the soil prior to compaction until it is not fluffy or loose, using either the manual compaction rammer or a 2-inch diameter cylinder. Following compaction of each of the first 2 layers, any soil adjacent to the mold walls that has not been compacted or extends above the compacted surface shall be trimmed. For the 4-inch diameter mold, compact each layer with 25 blows. On the first fill, the soil should be at least half full. Using the soil with greater moisture content, repeat the addition to fill the second layer. In operating the manual rammer, take care to avoid lifting the guide sleeve during the rammer upstroke. Hold the guide sleeve steady and within 5 degrees of vertical. Apply the blows at a uniform rate of approximately 25 blows per minute, and in such a manner as to provide complete, uniform coverage of the specimen surface. For the last time, with soil of greater moisture content, repeat the addition of soil to fill the final layer. Following compaction of the last layer, remove the collar and base plate from the mold. A straight edge tool may be used to trim the soil adjacent to the collar to loosen the soil from the collar before removal to avoid disrupting the soil below the top of the mold. Carefully trim the compacted specimen even with the top of the mold by means of the straight edge scraped across the top of the mold to form a plain surface even with the top of the mold. Initial trimming of the specimen above the top of the mold with a knife may prevent the soil from tearing below the top of the mold. Fill any holes with the top surface with unused or trimmed soil from the specimen. Press in with the fingers again and scrape the straight edge across the top of the mold. Determine and record the mass of the specimen and mold to the nearest gram. Remove the material from the mold and obtain a specimen for water content by using either the whole specimen or a representative portion from the top and bottom. When the entire specimen is used, break it up to facilitate drying. Otherwise, obtain a portion by slicing the compacted specimen axially through the center and removing about 500 grams of material from the cut faces. Obtain the water content in accordance with Test Method D 2216. This correction may be made to the appropriate field in place density test specimen rather than to the laboratory test specimen. Plot the 100% saturation curve. Calculate the dry unit weight and water content of each compacted specimen. Plot the values and draw the compaction curve as a smooth curve through the points. Plot the dry unit weight to the nearest 0.1 pounds per feet cubed and water content to the nearest 0.1%. From the compaction curve, determine the optimum water content and maximum dry unit weight. These are the typical results of the standard Proctor test. From graph 1, it can be seen that the data points, when connected, closely resemble the parabolic curve. According to Das, this finding effectively puts the compaction curve in a category known as bell-shaped, also known as type A compaction curve. Specifically, it falls under the sandy silt bell-shaped category. This suggests that the compaction curve of the soil sample follows a parabolic behavior, wherein the dry unit weight increases as the moisture content increases until such time that it reaches an optimum moisture content, and after which the dry unit weight decreases as the moisture content increases. In our experiment, these two crucial range of values may be retrieved using the parabolic equation as shown in graph 1. First is the acceptable range of moisture content in percent from 10.16 to 19.61, as well as the acceptable range of dry unit weight in kilonewtons per meter cubed, from 16.67 to 17.55. From the aforementioned result,